Wheels, not just on regular cars, but on race cars like F1 cars, play a hugely important role to their aerodynamics. In fact, because F1 cars have exposed wheels like this, they play an even larger role. And the main problem with wheels is that their geometries are pretty much fixed, like they have to be round and that's about it. So trying to change the aerodynamics is really difficult, and usually we're just left with controlling it more than changing it. And that is why how we feed air into them and where we put the grooves. In this podcast, we're looking at the aerodynamics of wheels and then extending it to F1 cars and their wheels. So does the wing system and nose of an F1 car, for example, affect a wheel's aerodynamics and vice versa? And something really cool is how the front wing element you find on F1 cars not only controls the wheel aerodynamics, but also how the wheel affects the front wing structure too. And that is because there's this feedback loop, as we will see. And as fast as F1 cars are, they aren't supersonic yet. So downstream elements still affect upstream elements, and we're still in subsonic flow as well, incompressible. So to look at all these aspects, we're going through this paper called Computational Investigation of the Aerodynamics of a Wheel Installed on a Race Car with a Multi-Element Front Wing. So this is open access, and you can find the link below. So to determine the aerodynamics of an exposed wheel, and then that wheel set up with a front wing system, these authors use CFD, which is great because you get a lot of details. However, there are many things that you need to consider when you're using CFD with wheels, as we'll go through. So first of all, they use the K-Omega SST terminus model, which is great. That's a good job there. One thing I want to touch on is the K-Omega SST equations, which is where they've mentioned below equation 7 here, so this line here. So for those who don't know, when you're using RANs, URANs, and DES, whether that is regular DES, DDS, or IDDS for CFD, you need to use some kind of mathematical model to approximate the turbulence in the system. And that model really makes or breaks your CFD. The reason why is because if you don't have this set of equations, then you'll just have a laminar flow, which doesn't really approximate most real-life situations. So what we need to see here is equations 3 to 7, and this is the terminus model in general. This is the K-Omega SST terminus model. And it's a little daunting, but these researchers actually do a really good job concisely explaining what they are. So in essence, these equations just indicate how much thermokinetic energy is produced at any given point, and how much is being destroyed at any given point, so the dissipation. And that's pretty much what these equations boil down to. Now, the final line below equation 7 here, that I was talking about before, is the model constants. And the reason why I want to talk about these constants is that I get asked about them quite often. So the interesting thing is that anytime you do CFD, it's almost guaranteed that the software you're using has these constants in there in the advanced settings. And there's a good reason for that. The reason is because they are advanced. But the reason why they are advanced is because they are heavily influenced when the CFD will predict that the boundary layer is turbulent or not. So they can dramatically change your CFD results. If you change these numbers, you could greatly alter where the boundary layer will transition to turbulence. They also affect vortex production, flow separation, wall shear stress, and the list goes on. So you really shouldn't change any of these values from their defaults unless you have good reasons to do so. The question then becomes, well, when do you have a good reason to do so? The answer is really if you have research showing you that they should be changed for your particular setup. So to elucidate that more, these numbers have also been found through experiments. So one way is you stick a hot wire into the flow and then measure velocities and fluctuations along an object. You can then deduce these constants from these experiments. Now I said along an object. The thing is that these constants change from object to object and from test condition to test condition 2. So in reality, these constants usually aren't for one specific setup, but rather to give approximate setups in general. So these numbers here, you just use on average. That means that if you can find research on your specific object, whether that's a tire or a ball or whatever, then you should potentially use those constants that they have determined. Now, one really important caveat is that the experiments need to be really accurate because the terminus model is crucial to accurate CFD, and these constants greatly affect the terminus model. So if you futz around with them and use less accurate numbers, then the CFD will greatly suffer. I mean, I'm really trying to stress to you how important these constants are, how they can change separation, turbulence, really everything in your simulation. And that is why you should really leave them alone unless you have good reason to change them. In fact, a good exercise actually is to go to your CFD and see how accurate it is and delicate it is on these numbers by running a simulation with the default numbers that you have, then change some of them to something else. then run the simulation again. You'll see how they affect your results and you'll be surprised. And in fact, actually, you might not even be able to converge your simulation because it will just crash. Also, before you do that, you should make a note of these numbers so that afterwards you can change them back. Anyway, let's move on to their CFD setup because there are many things we need to consider when we are CFDing wheels. And it was actually once my job to CFD wheels. So in figure 1, we see their domain, and they have a single wheel, and they say that the domain is large enough not to influence the wheel's aerodynamics. And I would generally agree with that. I would maybe make the height and width a little bit greater and put just a bit more touch distance between the inlet and the wheel, but it's pretty decent overall. Oh, and I should say that I mentioned, I just saw that they referenced my work here, and that's nice. I'm not going to tell you which one it is because apparently life is a lot better when people don't know who you are. So I want to stay anonymous there. Anyway, I didn't just circle which one don't worry about it. Anyway, in figure 2, they took a somewhat interesting approach in that they use an unstructured mesh. You can see in the left figure here, these blue shapes. Let me zoom in a little bit, actually, it'll be easier to see. Here we go. So all these blue shapes. For those of you who don't know, these blue shapes are actually the cells around the wheel in this particular plane slicing through the wheel. CFD meshes are actually quite bizarre the first time you see them. I remember sitting in my supervisor's office once, the first time I ever saw them really, and he was looking at this paper that I'd brought, and a picture of them had this mesh. And he looked at it and nodded along with its description. And I remember just thinking, how do you even understand what this figure means? It doesn't make sense, it's just a mess. But once you realize what this mesh means, this figure, it becomes very easy to understand. So this figure is literally showing all these different side cells. You can see they're very large towards the edges and get much smaller towards the wheel. And that is the refinement to the surface, and that is to capture the geometry better. Now, this is an unstructured mesh, and you can tell that because how these cells are dotted around in a random fashion almost. If they were like a grid-like setup, then that would be structured. So it would be like much more like rectangles everywhere as opposed to these little triangles. So the difference in terms of benefits for the unstructured compared to structured is that the unstructured mesh resolves the geometry much better, so you can pick up curved surfaces much more. A structured grid doesn't do that as well, but you use fewer cells in your mesh, so simulations are quicker and you don't need to use as much computational power to do it. Also, structured grids are quicker to mesh than unstructured grids, even if you have somehow the same number of cells. So those are the general trade-offs. Now, the figure on the right, if we scroll to that one, this shows us the surface mesh, and that shows us how well they picked up the contours of the geometry. So in a wheel, for example, we have quite a few sharp edges, quite a few rounded edges. Unstructured meshes are good for picking up all these different little features. And here they did a really good job. Overall, they had a 15 million cell mesh, which is quite a lot for just a single wheel. And in my experience, over about 8 million cells tends to yield a mesh-independent result. Now, they don't give a mesh-independent study here, which isn't great, but 15 million cells is pretty boss to begin with, so I think it's okay. And from my experience, this should be fine. Now, the term intensity is 0.2%, which you all know my thoughts on such a low term intensity for anything automotive. It's too low. But I can understand that they use this value because this is a prime wind tunnel value. Now, the velocity was 12.85 meters per second, which is about 29 miles per hour, and the Reynolds number is about 530,000, which would almost certainly result in a fully turbulent flow, even at this low term intensity level, because there are a few ridges that are around the wheel that will trip the boundary layer. Now, they only operated in RANS mode and not URANS, so that isn't great. Now, in addition to that, they have a semi-validation process. Like it's a little bit strange. So in figure 6, if we go down there, we see the values for the drag, lift, and pressure coefficients for their wheel, and they compared it to 2 published results. They compared both stationary and rotating, with the blue and red respectively. Now, the reason why this is a little dodgy is because the exact same wheel wasn't used between these different setups, at least from what I can tell. Now, if I'm wrong about that, let me know in the comments below, but I think the wheels are a little different. Now, as such, a proper comparison can't be made. Overall, the main takeaway is that they found that when the wheel rotates, so the red column, the drag drops a little and the lift drops a lot. And these drops are around in line with the literature too. But again, an exact comparison can't be made here. However, what I'm about to go through next will highlight how honestly, when it comes to wheel validation, it's kind of pointless. So the reason why is the following, or are the following. Now, there are many different wheels out there. There are so many different operating conditions too. So to give you an idea of the variability of this particular geometry, for a wheel, you can have different grooves. They can be different depths, different widths, different placements, and even different wear amounts. They all affect how much the flow is being channeled around the wheel and how. Then you even have the writing on the side of the wheel. So for example, if you get a Pirelli wheel, that brand, Pirelli, that will be on the side of the wheel, like engraved on, like either it's going to be jutting out or like recessed in. That writing can affect the flow. It can trip it, or it can even cause a separation around the side or change it. Then you have the temperature of the wheel. That affects how much the wheel flexes. That changes the bulge size around the ground, as well as how much the tire stretches and contracts due to the centrifugal forces as it rotates around, as it spins at very high speed. You also have the loadings on the wheel, which also change the bulge. So depending on how heavy the car is, what it's loaded up with, even how much gas is in the tank. You also have how much the wheel is tilted. So in figure 2, just around here we go. We see the wheel is tilted to the left a little. That is normal, and it changes from car to car, including F1 cars. Each team has their own tweaks. That all affects the flow. Then you have the edge of the wheel, which is called the shoulder. So this part around here, between the green and the blue. Depending on how sharp and rounded that is, the separation pattern changes too. So these variables are just for the tire, and we've even talked about the spokes. We haven't talked about them, or even the construction of the tire itself, like the various layers inside it. So taking into account all of these variables means that you even have to validate your CFD, that would be really only applicable to one exact tire you have, and that particular condition. As such, having a general validation like that what they have here, where they get about the same results, is arguably adequate right now because this is just a general investigation. So overall, I think these simulations are pretty good. I think the flow structures will be fine, and any changes to the drag and lift above maybe a few % will be fine. We'll need to see a bit later. Oh, and I also forgot that the tire surface roughness also changes things too. So there are many things, and these variables are just the ones off the top of my head. So this is the CFD setup, and one software you can use to do simulations like this is OpenFOAM. If you want to learn OpenFOAM, which is completely free but hard to learn, then take a course and link below. Now on to the rest of this research. These researchers were interested in the wheels aerodynamics, but they were also interested in differences between the stationary wheels and the rotation wheels. So how does rotating the wheel affect its aerodynamics, both in the lift and drag, but also the flow structures? So this investigation has been done before, this type of thing, where you're looking at differences in rotating and stationary wheels, but it is also good to have a regression to go through in a CFD, because a stationary wheel is quite a bit easier to simulate than a rotating wheel, and it's much easier to simulate than an entire vehicle and an F1 car. Now, one thing I'm not too sure about is how they simulated the rotation of the wheel. So there are many different ways you can do that, and they say that the wheel's surface had an angular velocity of 41.42 radians per second, which is what it would be about at 12.85 meters per second, the flow speed. However, it doesn't quite tell us whether that means it's a rotating wall boundary condition, an MRF, or a sliding mesh approach. From their mesh in figure 2, I'm pretty sure they didn't use a sliding mesh approach, because if they had, then there should be a distinct box around the wheel where the cells merge. We don't see that. Instead, the cells just steadily continue towards the wheel. So that means that it was either a rotating wall or MRF approach. And based on this one-line description, I'm pretty sure that they are referring to a rotating wall boundary condition. And for this particular case, that is actually a pretty good setting, because this wheel doesn't have any spokes and the longitudinal grooves are more or less axisymmetric. So approximating rotating with a rotating wall boundary condition should be fine. Now, I'll actually just briefly describe what a rotating wall boundary condition is. And what you're doing is effectively telling the CFD software that the wall is rotating at this particular speed, which is 41.42 radians per second here. It then factors that into the equations and applies the resulting forces on the fluid next to the wall. One thing that is always murky, however, is that when you use a rotating wall boundary condition, is that the surface roughness is never taken into account, and that could definitely affect how much force is on the surrounding fluid. But okay, it's okay in general still. So let's move on to the flow structure validation. As we saw earlier, they didn't have a strict force validation section, just a general one. And I think that that is generally fine for this study. One really good thing is that they have a flow feature validation study. And that is really good because when you get even similar or even the same forces, that's great. But at the end of the day, you could be getting those same forces for different reasons. So checking the flow structures to see if they are the same now provides you with much more certainty about the forces that you're getting and that they're actually accurate. Anyway, in figure 3, we see the flow structures of the isolated stationary wheel. The streamlines show the velocity from 0 meters per second to 20 meters per second, and the gray goop around the wheel is the vorticity isosurface. So in effect, it just shows the vorticity above a certain amount, and I'm not sure what value that is because I don't seem to give it. Now, they do use some strange terms when describing the vortices on this wheel. So for example, they call one on the outer, like this one here, the outer, let me zoom in a little bit. This is the outer vortex, they call it, but this is typically called a jetting vortex. This is a vortex at the base of the wheel on the outside. And the reason why this forms is that the flow around the bottom outside of the wheel rushes around and rolls up into this vortex. This is a very common vortex, and pretty much you see it on all cars. And anyway, we do see that this vortex here is forming, which is good, that's expected. They also have 2 vortices forming over the rear of the wheel and extend all the way down to the ground. That's pretty common as well. In fact, it's very common for wheels. So that's really good too there. Now in figure 3, we see the wall streamlines, and this is for the stationary wheel again. And looking at the front edge, so this front part here, the streamlines are straight. So that tells us that there is no separation there. So this edge is round enough to keep the flow attached. And again, if you have a wheel with a much sharper front edge there, the sharper shoulder, then that will change the flow again because it may separate. So that again shows us the variability of a wheel's aerodynamics. Now in figure 5, we see streamlines over the rotating wheel, and for anyone familiar with the Magnus effect, you won't be too surprised with these findings. So in figure 3, we see that the streamlines over the top stay attached. They shoot down quite a lot actually, and that's pretty cool. But as you get to the rotating wheel in figure 5, the streamlines detach almost at the top and then circulate around a little bit before shooting downstream. So they don't go down, and they pretty much detach right at the top of the wheel. The reason why that happens is because the wheel is rotating forwards. So the flow over the top now has more resistance from the wheel shear, from like pretty much just the friction with the wall. That decelerates it faster and makes it detach right there. And I mean, in figure 3, you can see that the streamlines are much redder as well. So they're like reddy yellow as opposed to blue around here for figure 5. So that shows us that the flow around the top for figure 5 is much slower than for figure 3. So that is a major difference in the flow structures between the stationary and rotating wheels. And this effect also occurs with the Magnus effect. And in figure 6, we see the forces, the coefficients for the drag and lift for the 2 different wheels. And the rotating wheel produces quite a bit less drag and a lot less lift. The flow separation over the top of the wheel strongly agrees with that lift reduction finding too, so that's pretty good. They all line up. So from all this, it seems like the general trend of the CFD very good. And given all the variables the wheels could have, I think the forces are fine here to generally trust, because there is never going to be one single wheel that represents all different wheels. And I'm almost certain that the 15 million cell mesh here is independent. The room is covered, so the rotating wheel boundary condition is fine. So again, I would expect that the forces anywhere between a few percent and 5% changes will be trustworthy and above. So that is an isolated wheel. What about when you put an F1 style nose in front of it, like this? Now that CFD gets much harder, and these researchers investigated that too. Now in figure 7, we see the domain, and they only simulated half of the car. So they cut it down the middle and only did the front half, the nose and the wing system and the front wheel. And they also didn't simulate past the nose here. That's one thing to make note of. One thing to note is that this front wing setup is considerably more simple than a modern F1 wing setup. However, again, because of the variability in the wing setups in F1, I think this is still fine here for a general representation. Something I don't like, however, is that they say that in another paper, this CFD setup has been validated. They say it just around here, this line. That's all well and good, but I would have really liked to see it here too, and that is because it is vital for this work and it should be included still, but it's not. Anyway, in table 1, if we scroll down here, we see that they simulated different cases. Case 1 is just the nose of the car without any suspension or wheel. Case 2 is the complete setup, but with a stationary wheel. And case 3 is with the complete setup and a rotating wheel. So we see the difference between just the nose and then the nose and the wheel, and then the nose, wheel, and rotation. Now the CFD ranged from 34 to 45 million cells, depending on which case we're using. And I don't know, again, if it's independent. They say it was, but no details are given. Here, 35 to 45 million cells seems to be pretty decent. So I guess it's okay. I'm not too sure. I need to see more details on it. Anyway, in figure 8, we see the mesh, and it's quite impressive from this figure. Something that stands out to me is that under the wheel, if we zoom in, here we go, you can see a yellow rectangle. And this is usually a wheel drive unit, which is what you use in a wind tunnel to rotate the wheel. So for the CFD, I'm almost certain that they used a rotating boundary wall condition, which means that nothing is rotating. So I'm not exactly sure why they have this wheel drive unit here. Perhaps this setup comes from another study and they just kept it. Anyway, they're now traveling here at 70 meters per second, and the turbulence density level is now 5%, which is much better compared to real-life conditions. That's much more accurate. Now in figure 9, we see the 4 cut planes that they're going to show data on in the CFD, for example, in figure 10. And speaking of figure 10, let's go there now to see their results. So for case 1, where we have only the front nose, no wheel and no suspension, the left column here shows that this entire setup is very streamlined. So the only region of somewhat bad flow is in plane B around the ends of the wings. Let's zoom in a little bit here. Here we go. It's a bit fuzzy, but if you download the PDF, you can see it a bit better as well. So anyway, around the ends of the wings in plane B, there is some pretty bad flow, and that is to be expected because you can see in figure 8, the elements here don't have any end plates. If we zoom up to figure 8, here we go, there we go. So no end plates on these little structures around here. So you have downforce being produced by these end plates, and there is going to be vorticity and vortices associated with that. And that's what we're seeing here with these small black arrows. They're rotating around in these circles, and that is the vortices. That will incur a little more drag, mainly in the induced drag. Now in the second column, we see case 2, which is where we have now the wheel and suspension, but the wheel is stationary. And immediately in plane A, this is really cool. So we see that the flow upstream of the wheel, well upstream, and even the nose element section is slower than in case 1 with no wheel. So that tells us that the wing system will have to deal with a different flow, that the wheel is now changing the flow upstream quite a lot, mainly because it is incompressible flow. And plane B shows us that the wheels, here we go, with the wheels, the vortices from the ends of the wing system are now pretty much gone, and that shows us just how much the wing system depends on the wheels to function optimally. And designing the wing system without the wheels in place won't give you the best results. They need to be done together. Now in plane C, we're now behind the wheels, and the wheels' wakes are really pushing close to the ground in a way that is good in that you can move it away from the rest of the car. That is generally good because you don't want to ingest this pretty bad flow underneath the car and spoil the downforce you're producing, unless you've designed your car to do that, but usually the cars don't operate very well with this pretty crappy flow. Then in plane D, we see that there are really only 2 wakes from the wheel still visible, and they're both from the jetting vortices, one on each side of the wheel. Now in case 3, which is the right column here, we now see what happens when we have wheel rotation. And honestly, there's almost no difference between wheel rotation and stationary wheels, which is pretty cool. Maybe only in plane C we get a main change, which is that the wakes are squished a bit more when you have the rotation of the wheel. Apart from that, all the major features are about the same. Now in figure 11, if we come down here, we see a vortex off the suspension. At least that is what the authors say. And I personally am not completely sure that this is the case. I don't think it's from the suspension. I actually think it's from the wing. The reason why is because, first of all, if I zoom in here, the suspension doesn't seem to be producing much of a difference in the pressures, I guess, or nor is it at an angle to the flow. So that isn't conducive to vortex production. There's not much reason for there to be vortices being produced. Secondly, if you were to look at where these streamlines are coming from, the black lines here, they come over the wing. We can see that there's this cutout on each side, and that's to the left of the streamlines and to the right of the streamlines on the left. So from here, the high pressure from over the top of the wing can now bleed over to the bottom's low pressure. And if you look at the left side of the figure, I think that makes a lot of sense because these streamlines turn towards the cutout region, as you'd expect, as they go around a little bit, the flow, and then spiral in the right way to indicate effectively a wingtip vortex. And it occurs here because of that cutout. So I personally don't think that this vortex is because of the suspension, but it's actually because of the wing here and this cutout right here. Anyway, in figure 12, we see the pressures over the nose and the wheels. First of all, I like the general comparison, but the color bars don't span the same ranges. You can see that they are different. They go from minus 12,500 to 4,000 compared to minus 13,500 to 4,000. So they're different ranges. That makes the colors harder to compare because they are different values. Also, this should really be in the pressure coefficient, not the pressure overall, because that would make it more applicable to other studies with different velocities. Anyway, overall, the pressure seems to be about the same. One main difference is that just over the top of the wheels, let me zoom in a little bit, over the top, there is a little higher pressure when the wheels are rotating, so this bottom figure here compared to the stationary wheel. And everything else looks pretty much the same. And that really agrees with the isolated wheel where we saw that there was higher lift for the stationary wheel compared to the rotating wheel. And that is because of this lower pressure compared to the higher pressure. Now in figure 13, here we go. We see the effects of the rotating wheel on this setup. And the good thing is that these trends are exactly the same as we saw with the isolated wheel. The rotation drops the drag and lift coefficients quite a lot. So that's nice to see how the nose and wing system don't really change these trends, and you can at least bank on that. And that is it in this podcast. If you'd like to hit the like and subscribe buttons, and this was all done in CFD. So if you want to learn CFD, and in particular OpenFOAM, which is completely free and easy to use software, but hard to learn, then check out our courses in the link below. Peace out, amigos.